Hey, thanks for attending another session by Decoding Research. Now, Decoding Research is a set of videos which typically talks about papers and primary research papers around AI and machine learning. In today's session, we're going to be talking about deep multigraph clustering via Attentive Cross Graph Association. Now, this is a research paper which came out in January 2020. As the name suggests, it kind of talks about multigraph clustering, and it's heavily indexes on attention-based mechanism and Cauchy distribution. We'll talk about that in a minute. Now we've used this research, paper in one of our products, and we've kind of evolved it to a point where we find this the research findings fairly useful. Quickly getting into the session, we've seen a lot of the data which is in and around us, mimic some form. Some of it could be graph, some of it could be non-graph. Now, graph-based data typically in terms of social media, network analysis, biology, and computer vision. Now, the fundamental problem when it comes to graph-based data is in terms of clustering. There's clustering. Once the data in the graph is being clustered, then it can be used for various decision-making process. Now, we've also seen there's a lot of data growth which has actually happened in the last decade or so, and resulting in a lot of large volume and intergraph based data, interdependent based graph data. Also, that's what we call as multi-graph. Now, what we've seen is the traditional methods today are more suited for a single graph, typically spectral clustering, modularity clustering, and stochastic block model. Now, when it really comes to clustering, multi-graph, the complexities are very many. One of which comes to my mind is obviously each graph has a different dimensionality in terms of embedding, and then trying to basically compare different dimensionality data obviously is a nightmare. Now, this session primarily kind of talks a little bit more in terms of the multi-graph clustering technique and primarily using attention as a mechanism. Now, obviously, now clustering in graph and identifying cross-graph relationship, there are a wealth of information. They can help you make a lot more better decision. Now, the problem statement. Now, why has multigraph really been a challenge so far? Obviously, the graph data is complex, nonlinear, underlying structures. Nonlinearity of the data needs to be considered while clustering. The modeling nonlinear representation has been a problem so far. Now, obviously, between Jan 2020 and now, there are some more papers which are actually came out around which primarily talks about multi-graph clustering. Different techniques are there, which I'm not going to be covering as a part of the session. Basically, interdependent graphs may be different topologically, sparse versus dense. And although intergraphs links are available at a node level, but how to correctly infer the hidden cluster association and use them for reinforcing the clustering accuracy. Now, what are we really trying to solve in this paper? So DMGC or deep multi-graph clustering based is based on a deep learning model and neural attention based mechanism. From that's what I've been telling you. All kind of repeated almost 3 or 4 times. Now, what does it really do? It proposes a deep learning method to simultaneously infer cluster assignment, probably and cluster association. In simpler words, if a node X in the graph belongs to a specific cluster, and if a specific cluster A has association with cluster B, and it's using some deep learning technique. Now, how is it done? Typically starts off the whole process in terms of taking the nonlinear data and pushing it through an auto-encoding architecture to kind of arrive the data space or slash embedding. At the same time, preserving the first and second order proximity between the nodes. That's typically the structure or around the node from a neighborhood standpoint of view continues to remain there because we obviously need that going down the line, right? Once having pushed it into a latent space where the embeddings are available, the next thing is to kind of go ahead and form the cluster. So you arrive at a cluster assignment probability for all nodes, and this is where the Cauchy distribution really plays a major role, and we kind of play around with the minimum entropy that helps do the job. Once having done all that bit of pieces, the next thing is obviously in terms of okay, now you kind of got your nodes and points which are assigned to a specific cluster. Now the next thing is that you need to obviously find out what's a cross graph cluster association. So while we do that, the third part of the problem is to kind of go and assign a cross graph cluster association using an attention based mechanism. Let's go under the hoods in terms of what's really happening, because this is where we're going to talk about the paper, the workings, the mathematics, and we'll also leave the last part in terms of the actual code base. Before we kind of get into the paper, there's some key concepts which are important from a paper understanding point of view. So the two concepts which have been used in the paper pretty heavily. One is the minimum entropy based clustering. Now, entropy, as you understand, is the randomness of information process. We've seen the entropy and the information gain in terms of decision trees, and it's the same thing out here. In simpler words, higher entropy or randomness means difficult to predict. So when it comes to clustering, it relates to class labels. A ground truth or lower entropy implies better clustering. Cauchy distribution, interesting. That's been around for a very long time. Basically, it's basically another. It's called as the Lorentz distribution, and is from the family of continuous probability. Yeah, but then there's a difference that it kind of resembles a normal distribution curve, but there's a difference. The difference really comes in the part that it has a taller peak than normal, and it has a fat tail of decay, which is where a lot of the findings will come in terms of reusing the fat tails for a lot of different purposes. So it's fat tail decay much slowly. Mentioned earlier in the paper, we tried to solve two things. One is a cluster assignment probability. It actually means that for node X in GFI to belong to a cluster K, there has to be a cluster assignment probability Q of IX, and QX measuring the probability of the node that X belongs to K. Once we kind of done the cluster assignment probability, the next we try to arrive at a cluster association property saying that cluster K in GFI associates with cluster L in GJ, and with CKIJ with CKL measuring the probability of cluster K. Now, having kind of been very clear on the inputs and what we're trying to get to an output point of view, now let's try to kind of go into the certain assumptions, certain the workings. Now, before we get into workings, we're assuming some things. One is obviously we've kind of put the graph through. It's been transformed. It's kind of gone through the autoencoder, and it's been transformed into this latent embedding. That means each node X in graph G of I has actually been converted to its latent embedding. Here, the latent embedding, what we're talking is H of IX, which is essentially a d-dimensional vector. And one thing we need to kind of note is that the di is the dimensionality of embedding space of gi. Now this is different for different i's. In addition to the cluster in gi, we also have we associate here the centroid vector for the cluster. We call it uki. Now, assuming that we have these things, obviously, later we'll kind of discuss an approach how to learn uki by an attention-based projection, but I'm going to leave that for later. Now, let's kind of focus more on the minimum, on how to basically figure out if the node X belongs to the cluster X, which is more of the cluster assignment probability. Now, so basically, the whole idea of what we're trying to solve out here is that we're trying to measure the similarity between h of I X and the K cluster centroid, what we call as mu K. Now, for this, we employ the Cauchy distribution of the kernel function. Now, as discussed earlier, comparing Gaussian kernel, a model-based on Cauchy, is more effective to force h of x apart from the centroid mu k if x does not belong to cluster K, which actually implies a very large boundary. So then we go ahead and define a score K IFX to indicate that the probability that a node X belongs to cluster K. Now the formula of this is actually coming from the Cauchy distribution. Now ideally, this is a uneven distribution, so you can see that q of x of I can actually run from qi all the way to x of qxki, and this is highly desirable, and it's basically that obviously the number of points many, that means the randomness in the distribution is high. So obviously so we basically we want to reduce the randomness in the distribution. So one way to reduce the randomness in the distribution is to minimize the entropy on qx of I. Now, if I really look at the entropy formula, summation of I1 to n pi log pi I think we kind of end up using the same formula for trying to determine the entropy for Qx of I. And so, kind of having out worked out the entropy formula, if you really take a good look at the entropy formula, it's in the form of x log x, which is nothing but a convex non-positive for 0 for x greater than 0 less than 1, and we have an equation which is kind of given out here in the form of x q x I and so on and so on. Now, if you really look at this equation, now if this equation, the equality really has to hold out, then qx, which is a one-hot vector, qi of xk has to be equal to 1, indicating. So this kind of indicates that it belongs to cluster K with a probability of 1. So this becomes our starting equation from cluster assignment probability. But apparently, story doesn't end up there. So now you have an equation to work with, but then minimizing of the entropy will result into a gradient exploding problem during the training of the gradient descent. So essentially, basically, it kind of gets to a point where qix of k tends to 0, the Bohr gradient tends to be very, very, very large, and which will dominate the gradient of the final loss and result in unstable results. Now, one way to solve the problem would be to go ahead and introduce an inner product loss. And once you introduce the inner product loss, you're probably going to get an equation of this sort, and where sigma is nothing but a sigmoid function. And so this becomes your final equation for cluster assignment probability. Now, once you've kind of gone ahead to complete iteration of the number of nodes and assign them specific clusters, we have so each cluster has enough number of nodes to kind of go and arrive at something what we call as soft frequency, which is nothing but an empirical distribution of the cluster. And let's say we have a soft frequency, so it'll be good to kind of apply KL divergence over the soft frequency and mu k, so and then eventually that's what go ahead and add it to the cluster loss, and this is what the final equation really looks like from a loss standpoint of view. Now, the next part is dealing with a lot of proximity constraints. Not going to talk too much about the proximity constraints. So typically, when you look at a specific graph, each and every node is going to have neighbor nodes, first order, second order, and there's a likely chance where if a node is connected to a set of neighbors, those neighbors would eventually be a part of the same cluster as well. So we've kind of gone ahead and derived two more equation for basically the first order proximity, and similarly for the second order proximity. I'm not going to talk much to it. At the end, there is a link to the paper, and there's a link to my blog which talks more on these proximity constraint. Having said this, now let's move on to the next part where we talk about cross graph association. Now, cross graph association is a third piece. So we kind of reached a point where we've gone ahead and assigned the nodes to various clusters. Now, obviously, we need to kind of look at the different clusters and see if there's an association between them. So, in this section, what we're going to talk a little bit more about. So, what we've developed is essentially an attention-based method to the model, which associates clusters between different graphs. So now, obviously, we talked about cluster UK for cluster K in GFI, and now so step 3 is more around cross-graph association probability, which is essentially a attention-based method. Earlier on in the session, we talked about mu k of I being assumed. Now it's time we go ahead and define that. Now, to preserve the autonomy of individual graph, mu k of I are defined in different embedding spaces for different GIs and which have different dimensional DI. This turns out to be a problem when it comes to comparison between centroids of different graph owing to the different dimensionality. Now, to solve this problem, we go ahead and define a unified space. This is a unified space for all cluster centroids of all graphs, such that each centroid is represented by a vector zk, which happens to be of uniform dimensionality d. And hence, since they have the same dimensionality d, then operations such as comparison become a lot more easier across the two centroids or multiple centroids. Now the question comes in terms of how do we really arrive at UK of I. So if you really look at this diagram closely, let's say we have Z1, which happens to be the the centroid defined in the unified space for cluster 1. Okay, and it so turns out mu of 1, mu 1 1 is essentially a projection of Z11. So in order to generate mu QFI in the embedding space, what we do is we perform projection from the unified space to the embedding space by for of each graph by a tension-based single layer fully connected network. So if you really look at Z1, it's kind of connected with C11, C1121, and so on with other multiple other weights. Now, essentially, this basically CKLIJ is a tension weight measuring the association between a cluster centroid K in GI to cluster centroid L in GJ, and such that if you really look at this thing closely, so mu K of I essentially turns out to be um, you know an attention based equation over a concatenation of all the centroids, okay, multiplied by zk's, that eventually multiplied by zk of I, and then wi, which happens to be weight of the single layer fc, and over out we perform a ReLU operation on top, and that's how we kind of arrive at uk of I. So I think now we kind of got to a point where we kind of defined UK of I. So moving on further, this is what we kind of talked in the previous slide, concatenating of all the centroids for all graphs over G of I via tension together with ZK. The output UK can capture all the cross dependency at a cluster level. Now that this is where the things start getting interesting. Now the tension weight CK of L, that is the tension weight measuring the association between cluster centroid of K in GI and cluster centroid L in GJ. It turns out we again start using the Cauchy distribution as a kernel to measure the association. Now, tension weights are directional by nature. So, for example, C1112 and C1121 exist between cluster 1 and 2. Furthermore, now that we kind of have the associations between cluster defined, now we kind of get to a point we would want to kind of regularize the findings so far that we had. So recalling the cluster assignment distribution of node x of graph gi is qx. Now intuitively, if x is strongly linked to node y in g of j, then the cluster of x and cluster of y are linked, likely to be associated. So that is CKL ij is large, and the two clusters are denoted by KLNN. Now, CKIJ is basically essentially an attention matrix, so scaled entry is CKLIJ. And then this intuition applies that two vectors QI and QI transpose are similar in certain metrics. Now, generalizing to the relationship in the case where X linked to multiple nodes, now let NX I to J be set of nodes where J of J, nodes in GJ which are linked to GI. Now, to penalize this inconsistency in the assignments, following loss function is proposed. So basically, it's qx of I and qx where I tends to j squared, and such that qx I tends to j is kind of given by this equation. And SF of x is a weight for intergraph linked dependencies in x of gi and y of gi. Your Q of Xi's, specify transfer cluster probability of node of X through node of Y that belongs to n of X I of J. Furthermore, let S of ij be a matrix with xi the entry and S of x ij performing a row normalization on to obtain S of ij. So summing up over all the nodes in the graph, the loss function looks something of this nature. So I won't kind of dig too deep into the cross graph regularization. Again, you can refer to the paper, which kind of talks to more of the detail, but I was kind of more interested in terms of just highlighting the L cross loss, from a cross graph regularization standpoint. Now moving on further, obviously we need to kind of get to a point of integrating the clustering losses, the proximity losses, the cross graph regularizer into unified objective function, because that's the at the end of the day, the loss function has to be applied altogether. So basically, it's min of theta, z, and w. Well, LC, alpha, L proximity, and beta, L cross. And alpha, beta are hyperparameters for trade-off between losses. Theta turns out to be theta 1 to theta 2g are the outputs for my autoencoder standpoint of view. Z is are the cluster centroids. W is the weight for the parameter for retention-based centroids. Furthermore, the algorithm, this is the algorithm from a deep, multi-graph clustering DMCG style. So, in inputs, we talk about the density matrix, number of clusters, cross-graph relationship if it exists, alpha and beta. The output is cluster assignments, cluster associations, and we initialize, theta, W clusters, centroids, and Z, and we kind of go ahead while non-convergence too. We compute Qi. That's the first step. If we kind of go back to step one, we compute Ci of j, and then compute the loss, and then we update these parameters using Adam, and then kind of return, the Qi, basically, which is nothing but the cluster assignment, the cluster association. Furthermore, let's get into the code. So we talked about step zero. You know, that's where the inputs, which kind of talked to the previous slide. Step one is to feed the graph data to auto-encoding components, which are the node embedding, while preserving the proximity between the nodes, and that's what we call the representation learning. Step two is more around deriving the similarity probability for each node, embedding in the graph cluster, which kind of decide if the node belongs to the cluster. This is where the Cauchy distribution comes in. So basically, it's a node assignment layer. Step three is a cluster association probability with respect to other clusters of cross-graph linkages. Now, this is where the attention mechanism comes together. Now, considering this is a deep learning method model, it has to be trained with a joint loss function, which we kind of talked to right at the end in the cluster and the attention weight. That's the regularization piece. Now, that being said, this is the GitHub code link, which you can find the working code for this. That's it. Now, thank you very much for comments and suggestion. Reach out to me at asolanki77 at gmail.com. Thank you.